So I think we are up to so-called 3D transform, 3D or whatever dimension is. It's just that once we define that we transform in one variable, you can extend that to any number of variables, right? Now, because it's in higher dimension, it's not using time, it's not using t, right? And not t and omega now. It's just going back to k. So basically, uh, going back to our linear case, I mean single variable case, the inverse Fourier transform is like that. You have to just use the language of the textbook. And in this case, let's actually use a minus sign. Times x and pk. This is the inverse Fourier transform, and then the Fourier transform t sub k is using the symmetric convention. It's just the same form, except this exponential function, right? That's the Fourier transform, inverse Fourier transform. Okay, and yeah, that verb doesn't matter. You can change it. Instead of using k, you can use omega, and x instead x you call t. It's like time and frequency, but k and x like more like the wave number and displacement. That doesn't matter. Whatever you use, whatever variable is just the same. Except that sometimes the people using different sign conventions. I mean, like usually in omega, we like using this kind of sign convention, but in K, we'll put the negative sign here, positive sign here. But your textbook using that, so I follow your textbook. I mean, not everyone, like Jackson using what I said in E and M, Jackson using what I said. But it doesn't matter. So whatever the I and minus I, and even some people define I and I differently. So as long as using, and when you do some one derivation, if in that derivation you keep your conventions consistent, then the final answer in the real physical property will be the same. Okay, so after you do all the Fourier transform, how you define how you choose your convention doesn't matter. Okay, and now the idea is if f is not just depends on one variable, it can depend on many variables. It depends on x and y. Then obviously, so it can depend on x and y, right? And what you do is just multiply by doing it the same thing for both x and y. So that becomes a square. And this becomes, it depends on case of x and case of y. This becomes case of x. So you basically now you need to add another term, case of y, and this you need to be. And likewise in here, the square. This is case of x, case of y, right? This is fx and y. And this. Right. So you get the idea. So whatever number variable, if your three-dimensional space is at another one, basically, and so on. At another one. Okay, and so you write it like a vector form that you can apply to whatever dimension. So yeah, x. Yeah. Assuming it's 3 dimension, it's 2 pi, 3/2. And this is multi-dimensional integral. So you put the Fourier transform. Now it depends on wave vector k, however number of component you have, and this exponential function become I minus I k dot x. And then this is n-dimensional integral. So using the language of your textbook is so if 3-dimensional is CQK, and the Fourier transform right. For 3D, it's like that. For 4-dimension, it's just add. Sometimes you do 4-dimensional Fourier transform because you have three spatial dimension and one time dimension. If you do a Fourier transform all space and time, you have 4-dimensional Fourier transform. That's also fine, except that sometimes we separate the omega out, but not always. When you talk about relativity, after you learn about all the relativity, it's just to get like 4-dimension. Okay. All right, so that definition is straightforward. There's nothing more, except that the sometimes doing this integral, some will involve some special technique, which you can only do it case by case, by example. I mean, more than one specific trick you can do. All right, it's okay. So the definition, okay. So the rest is just examples. See how many of them. Now, the first example is this exponential function divided by r. So this example is e to the minus r. In spherical coordinates, so r is the radial component. Okay. So basically, we can say that r is the usual radial component. So right, so that's fine. All right, so you want to calculate Fourier transform, except that now your textbook changes to another location. Instead of calling it G, use this square bracket notation. It actually doesn't matter. The Fourier transform of this one. It's just like what we did before, just the 2 pi we have, and put it in a spatial integral of this function. And then multiply by e to the pi k dot x. Okay, that is what you can do. And the textbook, the way your textbook do also involves something that we have to skip because the order of the what I going through it is different now. You haven't learned all this speaker harmonics yet. The textbook user identity to explain the 1 over r in speaker harmonics to all those y, and n. And so we won't follow it. It doesn't have to. No, it's actually give you an example of a common trick to do this kind of higher dimension integral, especially in 3 dimensions. Okay, so we just going through a 3-dimension integration. It's not too long. You should separate that into the one element in spherical coordinate. So the one element is r squared. So hopefully remember. Theta is the spherical angle, phi is the azimuthal angle. Define the 3-dimensional space. And over here, it's any vector along R So the angle between C and R vector is theta. The projection on the xy plane, the angle between x and the projection is with the azimuthal angle phi. Hopefully you remember all this. Right? So, all right, so the element is volume element. This is dqx, right? And then you just need to integrate accordingly. So the volume element you L squared dl, and the integration limit is 0 to infinity, obviously. This is positive, and positively definite. So it's 0 to infinity. And then we have sine theta, d theta. And then for theta is from 0 to pi, because that's the range of the azimuthal angle. And phi is just obviously 2 pi, 0 to 2 pi, the azimuthal angle, right? And then you have this function into the result O divided by O, and then you have I k dot x. Now we can do a common trick, because k is a given vector. So, so for any given k, that is, and this function doesn't. This function only depends on radial distance. So you rotate your coordinate system, it doesn't change the length, doesn't change R, doesn't change. You rotate. So basically, you can rotate your coordinate system such that k is along z direction. All right. So this k dot x becomes k r cosine theta, because x is, this is the x vector, right? X dot into k will give you k magnitude times r magnitude, and then times the cosine of the angle between the cosine theta. Okay. Good. All right. So that's not too bad. And first thing you see that it doesn't depend on phi. Everything doesn't. So you can integrate phi out right away. So it's one of the. I mean, it's 2 pi, so cancel part of this. It's just square root of 2 pi here. And there's a cancellation of r with one factor in this r squared. And then you do a common trick that cosine theta d theta is d cosine theta, or minus d cosine theta. You can, if you like, you can write a new variable. It's like a to defined as cosine theta. Would be a minus sine theta d theta. And the range of that is theta is 0 is 1. Theta is pi is -1, so it's -1 to -1, but there's a negative sign. So you can use the negative sign to flip the range of theta from 1 to -1 to -1 to 1. So this is, that's keeping the R on the, and then this becomes the A here, -1. A here is cosine theta. Okay. And this is minus R as I K R A here. And so what coefficient? We're calculating the Fourier transform. There's no n here. This is my new definition eta. I define a new verb eta as cosine theta, and then I change the integration variable from theta to eta. So d theta, instead of d theta, I use d eta, and then yes, sine theta d theta, sine theta theta is minus d eta. But the range of eta is originally is 1 to -1, but I use the -1 to 1. This is very commonly used. I just going a little bit faster than. Fourier transform of this function. Yeah. Yeah. Okay. All right. So let's see. Okay. I mean, still have 7 minutes. Okay. So just go ahead and then the this factor can pull out. Out, out, out. And then this integral is elementary because exponential function. So it's exponential function beta divided by 1 all. Right. And then you can cancel that out here. And ik can be taken out of the integral. 1 over I square of 2 pi and to infinity. And when this one is e to the ikr, when it's minus 1 is e to the minus ikr. This is the lower limit, so this is positive. Lower limit is negative. You already pull out the ik here, right? And then, so there are two terms. You have e to the minus alpha plus ik r minus e to the minus alpha minus ik. Yeah. Okay. Now these twos are all elementary. Yeah. Keep going. Hopefully we can finish it today. Okay. Copy everything. And two terms. One is e to the minus alpha plus ik divided by minus alpha plus ik. And then second term is e to the minus alpha minus ik divided by minus alpha minus ik. And everything is evaluated. Infinity. Okay, at infinity is trivial because you have the minus alpha. Alpha assumed to be positive, otherwise this is divergent. Okay, so the upper limits are all 0. The lower limit is just 1. Both terms are 1 because substitute r equals 0. Both are 1. And there's a negative sign, so you can use it to flip this, or you can flip the I also. It doesn't matter. So you use this to flip the sign. Is the lower sign of the lower limit to flip the sign, so it becomes alpha minus ik. Alpha plus ik. And the two terms is alpha plus ik minus alpha minus ik. Right? And now you cancel yeah, I cancel with alpha, and then you got 2ik. Okay, 2ik in the numerator, and cancel ik become a factor of 2 pi. And the denominator becomes alpha squared plus k squared. This is the answer. This should be 20.41. Yeah, because the textbook writing is different. It's multiplied by 2 pi and divided by 2 pi. So the factor is different, but it's the answer. Okay. So it's just giving you some an example how you do some of the trick to do integration, because all these are very commonly used.